All right, let's consider adding 15 cubic centimeters of 0.1 molar HCl to a buffer, a 100 cubic centimeter buffer with the following composition. Zero 0.05 molar NH3 and 0.05 molar NH4 plus. So the concentrations of the two of the conjugate and its base are as follows. So let's remind ourselves of what's going on here. We've got NH3, which dissociates to form NH4 plus OH minus. When both of these are present in significant amounts, then the solution will act as a buffer. When I do buffer problems, the first thing I do is I figure out what the hell is in there. So what the hell is in there? And what did I add? And in this case, it's a fairly straightforward situation because we're told that we have, so for NH3, we're told that we have 100 cubic centimeters times 0.05, millimole, we'll say millimoles per cubic centimeter, and that gives us 5 millimoles. I'll just remind you that you can write, I can write it up above here somewhere so we can see it. Right, so if I write M, I'll put it in a little box, M is equal to moles per dm3, which is also equal to cubic centimeters per millimole. Or sorry, millimole per cubic centimeter. My mistake. Yeah. Anyway, we can come back to that if we need to, if that's the case. But anyway, these calculations look like this. And then if you take NH4 plus, we find that it's the same calculation. So we're just repeating what we did just above. We have 100 milliliters of the buffer. The concentration of the conjugate acid is 0.05. So this is millimoles per cubic centimeter, which equals 5 millimoles. So now we have to ask the question, what the hell did I add? Well, I added this amount, so 15, so this is HCl, which essentially means that I've added 15 cubic centimeters of 0.1 millimole per cubic centimeter, which results in 1.5 millimoles. Now we know what everything is. This is NH3, right? NH4 plus, and this we'll just simplify it to make it H plus. Fair enough. It's always really important when you do buffer problems to think of this being the initial conditions. It's easy to be confused by the fact that the buffer is already present. And you think, aha, this equilibrium has already been established, and so I have to find out what the OH minus concentration is before I add my the imposed change. And in this case, the imposed change is the H plus. What am I adding to this buffer? I'm adding H plus. Well, you can be easily confused into thinking that you should find out what's going on before you add this. Don't worry about this. Just assume that you're adding all of this to a bucket or a beaker, and it's all going on inside there at the same time. So from the start. So if I draw my beaker, right? Let's draw a beaker here. Ooh. Let's make it really big because it's not really a beaker. It's just a place where we're going to solve the rest of this problem, right? So here's our beaker, ooh, right? And inside the beaker, we have an equilibrium taking place, which is what is causing the buffer, or is what is the buffer, I should say. And that's our initial conditions that we wrote up there. Sorry, this should be minus. Okay, but then we have to think about what we did. Now what did we, our imposed change is we're adding H plus to this. So now I think, what are we doing when we add the H plus? What does it react with? Our instinct is to say, well, it reacts with this OH minus here, because the OH minus is there, and we think, oh, H plus, but it makes water. But that's a bad instinct for solving these types of problems. So we have to learn to think that acids react with bases. Acids react with bases, and forget about the OH minus, because that'll just create more mathematical headaches for us. So we have to assume that we're adding all of this stuff at the same time. And when we do that, we think of the imposed change. And then so let's create a thought bubble on what's going on and how we need to solve this. So we create a thought bubble, and this is someone over here thinking. I'm thinking, right? And inside the thought bubble, let's put together what we think is actually going to happen here. So we have the equilibrium. Let's go on, but then in our thought bubble we've added H plus, and the H plus is reacting with the NH3 because that's the base, and this reaction only goes in one direction, and it produces NH4 plus. We're going to ignore the OH minus because the OH minus is going to be generated when we go to equilibrium anyway. So then we think, how much of this H plus did we actually add? Well, we added 1.5 millimole. And NH3 we had 5 millimoles, which come from the buffer. And this is also 5 millimole. Since this is a chemical reaction where the two reactants are going to combine and get used up, right? Then we can say, well, we can see already that this is the limiting reactant. So we're going to subtract 1.5 from each of these, because this one goes away. And so this becomes 0. And 5 minus 1.5 is 3.5. And on the other side of the chemical reaction, if you take this away, then you're increasing this. So increase by 1.5 millimoles. This means that this is 6.5 millimoles. So you could say that, if we wanted to label this a little bit, this is the equilibrium that's taking place. And this stuff inside of our thought bubble is the, imposed change, right? And the imposed change is the H plus there. And then we have to figure out the consequence. So we need to find consequences. So now once we have this, we can recognize the fact that we can then rewrite this and determine the new equilibrium. So I'm going to write that in green here. We'll say new equilibrium. And the new equilibrium can be solved in several different ways, but we're going to use the Henderson-Hasselbalch equation to do this. Just like we did, or you can do when you do any kind of buffer problem. So what we need to recognize, though, is that technically we can't solve the Henderson-Hasselbalch equation straight from the molar amounts. So this is both millimoles. So if we write it up here, we can look at 3.5 millimoles divided by the total new volume, which is actually 115. And that's going to be the concentration of NH3. All right, the new one. And if we look at NH4 plus, it's going to be 6.5 divided by 115 millimoles per cubic centimeters. But when we look at what happens in the Henderson-Hasselbalch equation, we realize that actually we can get away with skipping this problem. Because we don't actually have to do these calculations. And let's look at why. So if we look at the Henderson-Hasselbalch equation for bases, we see that the POH equals the PKB plus the log of the BH plus concentration over the B concentration. Now, in our case, the BH concentration is 6.5 over 115. So we'll just write it in there. I'm going to write it underneath here. So POH equals, and then we can write in the PKB right away. It's going to be the minus log of 1.8 times 10 to the minus 5. And then it's going to be plus the log of, in this case then, 6.5 divided by 115 divided by 3.5 divided by 115. But since this fraction is divided by this fraction, and dividing by a fraction is actually multiplying by the reciprocal, we can cancel the 115. So it becomes 6.5 over 3.5. So the POH for this will be equal to the minus log of 1.8 times 10 to the minus 5 plus the log of 6.5 over 3.5. So if you do that calculation then, you find that the POH is equal to 5.01 plus some change, but it rounds to 5.01. Which means then that if you want to find the pH, you need to take 14 minus 5.01 will equal the pH, which will equal then, in this case then, 14 minus, which gives you 8.98 or 8.9, which is, yeah, that's essentially the change for this pH. The original buffer here is the subject of a different question, but this original buffer had a pH equal to 9.26. So you can see that even though you added quite a bit of acid at a fairly high concentration, the pH went from 9.26 to 8.9, which is a very kind of a small change. It's a change of 0.2457, something like that. Thank you.